You know, there's something that literally holds our world together, but it's usually hidden away in these super dense, complicated engineering tables. Well, today, we're going to decode that playbook. We're going to turn all that data into a story you can actually see and, really understand.
So what is it? Well, in a word, it's heat. Or more precisely, it's how materials react to heat. And believe me, this isn't just some random science class curiosity. Nope, it's a constant, powerful force that every single engineer has to deal with. If they don't, they're looking at catastrophic failure.
All right, so here's our game plan. First, we're going to get a grip on this unseen force we're up against. Then we'll learn the language, the lingo engineers use to control it. We're even going to do a little hands-on walkthrough of their code book, compare how different materials act, and finally, see how all this hidden data is shaping the world all around us. Sound good? Let's go.
Okay, first up, let's get a handle on this fundamental challenge. We're talking about a totally natural phenomenon that has enough power to bring down the strongest structures, if you don't give it the respect it deserves.
It's a super simple fact of physics, right? You heat things up, they get bigger. You cool them down, they shrink. A steel beam, a plastic pipe, a concrete sidewalk, everything is constantly, invisibly breathing with the temperature. And if you ignore this, well, things break. Badly. So how do you manage a force of nature? You don't fight it, you work with it. And to do that, engineers need a really precise language. They need data. So let's learn the two key terms that let them predict and control exactly how materials are going to behave. The first property is thermal expansion. The easiest way to think about this is as the how much it grows factor. It's all boiled down to a single number called a coefficient. A bigger coefficient just means a bigger change in size for the same temperature change. This little number is absolutely crucial. Okay, the second key property is modulus of elasticity. You can just think of this as the how stiff it is factor. See, a material might want to expand, but if it's incredibly stiff, it has nowhere to go. It can't just bend out of the way. So instead, all that force from wanting to expand builds up and it can become immense, totally destructive. It's the combination of how much it grows and how stiff it is that really tells you the whole story.
All right, so where do the pros get these magic numbers? They turn to standards, basically rule books, like the ASME B31.3 code. So let's crack open the codebook and figure out how to read what might be the most important page for this topic.
Whoa, okay. At first glance, I know what you're thinking. It's a giant wall of numbers. And you're not wrong, but it's also an incredibly powerful tool. This single page holds all the secrets to predicting how all these different metals are going to behave across a huge range of temperatures.
Let's just make this super simple. How do you actually use it? It's really just a three-step process, okay? Step 1, find your material over there in the left-hand column. Let's pick a really common one, carbon steel. Step 2, find the temperature you're interested in along the top row. We'll go with 150 degrees Celsius. And finally, step 3, you just trace them with your fingers till they meet and read the number for coefficient A. And boom, there it is, 12.3. Simple as that. You've just pulled a precise, critical piece of data from an engineering code, just like a professional. That one number, 12.3, tells an engineer exactly how much a piece of carbon steel will have expanded by the time it hits 150 degrees. Pretty cool, right?
But of course, our world isn't just built out of metal, right? What about plastics, other materials? Well, their behavior can be wildly different, which is why there's a whole different table just for them.
And this is where it gets really fascinating. As a rule, metals tend to have lower expansion rates, but they are very, very stiff. Nonmetals, like plastics, are often the complete opposite. They can expand like crazy, but they're way more flexible. Understanding this basic difference is just everything in design.
And this chart just lays it all out perfectly. Check this out. So carbon steel is our baseline. Now aluminum, another metal, expands almost twice as much at the same temperature. But then look at PVC plastic. Its expansion coefficient is a massive 54. It expands more than 4 times as much as steel. You can start to see why grabbing the right number from the right table is a pretty big deal.
Okay, so we've been geeking out on numbers and tables, but what's the big picture? Why does this matter? Let's zoom out and connect these little digits on a page to the actual world they help build and protect. You know, every time you see one of those little gaps on a bridge, that's not a mistake. That gap was precisely calculated using this exact kind of data. What about those massive pipelines that cross hot deserts? Without room to grow, the heat would create so much force, they'd literally buckle and break. So engineers use these tables to design these huge U-shaped expansion loops that safely absorb all that growth. It all comes back to finding the right number in a table.
This quote really just says it all, doesn't it? It's not just about numbers on a page, it's about responsibility, it's about safety, it's about reliability. Getting this right is everything. Getting it wrong, well, that's a disaster. It's a world of precision where every single decimal point matters.
So there you have it. We've decoded a small piece of the engineer's playbook. You now have this new lens to see the world. So the next time you walk across a bridge or see a long pipeline, you'll actually understand one of the powerful, invisible forces at play, and the hidden data that keeps it all from falling apart. What else is out there, hidden in plain sight, just waiting to be seen?